Hi, my name is Ray Daw, and this is my Lab 5. The big idea with this lab was there was a falling magnetic dipole through a tube of aluminum foil. Um, Obviously, the aluminum would act as a conductor. And so the B field from the magnet caused a curly E field on the loop being the aluminum foil, and the curly E field would cause an induced EMF in the loop, which would then drive a current, and this current would then cause an opposing B field um, coming from the foil and opposing the movement of the falling magnetic dipole. So the main concepts we used in this lab, first of all, was the Biot-Savart law, which pretty much calculates the B field um, from a dipole at any point relative to the dipole. And this was used to calculate the B field from the magnet on the aluminum foil at all the different points in our code. And then Faraday's law, shown in the second bullet, was used to calculate the change in the magnetic flux. And then for Newton's second law, we just use this to account for all the forces, so we could model how the dipole or the magnet fell through the tube of aluminum foil. So these are the different measurements I used or measured from the actual physical part of the lab. Over to the left was just the dimensions of the aluminum foil, as well as the mass of the magnet. And then over to the right is the time for the trials that I physically did, and the average is shown there below. And then using this data, we can kind of compare it to the coded data to see how accurate it is. So this is what I got for my coding, and starting with the top left, this was again just the dimensions for the tube, and then the second one to the left, second box, is pretty much just how the magnetic field was calculated at all the points on the ring, and then the bottom left was just calculating the flux through the ring caused by the magnet. And then over to the right, you can see the velocity versus time graph for how the magnet how the magnet fell through the tube. And as you can see, it pretty much accelerated the whole way through, but the acceleration slowed because of the opposing forces. And there you can see it kind of ends around 0.6 seconds. So if we go back a slide, that's not too far off from the actual data that we collected. So just to wrap up, a couple questions. Whether the resistivity of the conductor were reduced as close to possible to zero. Pretty much what this would mean would be that the current would be significantly higher, meaning that the induced magnetic field or magnetic force from the ring would be significantly higher, meaning that the magnet would fall a lot slower because the opposing force would be a lot bigger, and the magnet couldn't accelerate nearly as quickly. And then on the other hand, what if holes or slots were cut into the tube? How would this affect the ring's current in our model? Pretty much if holes or slots were cut in the tube, these would be considered regions where the resistance was pretty much infinite, as you can think of air as, a resistor, I suppose. And the resistance would be so high that no current could flow through those sections where there were holes. So this would just reduce the induced magnetic force, causing the magnet to fall faster. And that is it. Thank you.